Last time we started section 4.2, we're going to finish it up this time. We were talking about prime and composite numbers. We talked about prime factorizations, and I believe that we are on the fundamental theorem of arithmetic. All right, so in math, anytime somebody puts the word fundamental in front of it, usually means it's pretty important. Okay, just rule of thumb for you. All right, it says each composite number can be written as a product of primes in one and only one way, except for the order of the primes. For example, 15 is 3 times 5. We wouldn't say 5 times 3 is different. It's just ordered differently. It's the same numbers. So I'm not concerned about the order the numbers are in, but I am concerned about the fact that when I take the number 15, it's 3 times 5. There is no other prime decomposition of the number 15. And that's what the fundamental theorem of arithmetic says. When we break the numbers down, we will all get the same thing. We talked about the next theorem, or at least an application or a slight difference to the next theorem back in section 4.1. The next theorem, 4.4, says that if D is a divisor of n, then n over D is a divisor of n. And the point when I talked about it was talking about the fact that factors come in pairs. So if I had the number, 15 is fine, I suppose. Let me get a different color. 15, I can break it down so that it's 1 and 15, right? Like if I'm not worrying about primes, just for the moment, 1 and 15. Or I can break it down so that it's 3 and 5. But they always occur in pairs. And in particular, then, if it's divisible, say, by 3, then it's divisible by the pair that goes with it, which would be 15 divided by 3 or 5. Okay? So this is just telling you that all your primes, factorizations, not prime factorizations, but all your factorizations come in pairs. So if 7 divides a number, then there's going to be another number that goes with it that divides that number as well. If n is a composite or a composite number, then n has a prime factor p such that p squared is less than or equal to n. All right, so every composite number has a number lower than it that will actually, it's not saying it's a prime, so it says it's a prime factor of the number, that squared will be less than or equal to that. I'm trying to think of an example for us. Let's say we did the number 30. What's a prime factor of 30? 3 would be. And is 3 squared less than 30? Yeah. There's other numbers that are factors that are prime of 30 as well. For instance, 5. 5 would be a prime factor of 30, and 5 squared happens to also be less than or equal to the 30. So we're only guaranteed that there's going to be 1, but there's going to be at least 1. If n is a whole number greater than 1, and it's not divisible by a prime p, such that p squared is less than or equal to n, then n is itself prime. Now, this is actually a really valuable test, this one right here on 416, because what it tells you is it tells you how long you have to test numbers to decide if they're really prime or composite. So if I give you a number that's rather large, and almost any 3-digit number would qualify, I think, is that, but let's say I gave you the number 738. 8's not a good number. How about 737? If it ends in an even, you know you're done. It's not prime. But if it ends in an odd, you have to figure something out, right? What this actually tells you is it tells you exactly how far you have to go. You have to figure out first what's an approximation for, it doesn't have to be an exact value, for the square root of 737. So let's check it out real quick. What's approximately equal to the square root of 737? A number with 1 digit decimal is probably fine. Square root of 737. exactly?
No, point, like.
Okay, I was like, really? How did I do that? 27 point, what was it?
0.14.
Okay, 1's good.
Okay.
Okay, this tells you that as you're testing numbers to see if this is prime, you look at it and you say, nope, 2 doesn't work. And you look at it and you say 7 plus 7 is 14, 15, 16, 17. Nope, 17 is not divisible by 3, so 3 doesn't work. That the number at which you can stop testing numbers is 27. Whatever primes are less than 27 stand a chance at dividing the 737. Anything bigger than that won't. So you don't have to keep testing indefinitely. Okay? And I think I have the next one as an example. We're going to actually do one and see. So this one says, what is the greatest prime you must consider to test whether 967 is prime? So you check this square root principle. So if I take the square root of 967, what do I get? Approximately with 1 decimal. 31.1. So what is the biggest prime number smaller than 31.1? Because it actually asks me what prime number must I 29. I think there's one bigger. I think 31's prime, right? Okay. So the answer here would be 31 because it's the biggest prime number smaller than 31.1. So the last number we would test, if we kept testing, we could stop testing once we get to 31, and we'd be good. Example number 3 says, show that if 1 were considered a prime, every number would have more than one prime factorization. So we talked last time about the number 1. It's one of those weird numbers. I told you it wasn't prime. It wasn't composite, and we used the definition to justify that. Prime numbers have 2 factors, 1 only has 1 factor. Composite numbers have more than 2 factors, so that doesn't work either. And this is actually the problem with number 1 being sort of maybe considered prime, because you almost want to be like, well, I know she said that, but it's kind of like a prime. I know some of you are thinking that even as I said it. You're like, yeah, well, sort of. All right, so here's the problem if you would consider it a prime. We'll take the number 15. I know I used this number before, but it's a nice one to use. 15. What's the prime factorization for 15? What did I say it was? 3 times 5. All right. If 1 were a prime number, then 3 times 5 times 1 would also be a prime factorization. Right? I mean, if it's prime, that would actually work too. You are exactly right. This would be possible for any number, I'll write it to the n, number of 1s. That's not good. It's not good at all. In fact, if that were true, then this wouldn't be. Because the fundamental theorem of arithmetic says there should be only one factorization possible with primes. So this is another reason why we certainly wouldn't want the number 1 to be prime, is because then this fundamental theorem of arithmetic simply would not be true. All right, let me show you an application of factorization with an example 4. Example 4 says, Mr. Arbor wants to plant apple trees in a rectangular array. Okay, so rectangular array, we know what array models look like. If he has 36 saplings, find all possible numbers of rows if each row is to have the same number of trees. What is this asking you to do? Find factors of 36, and find them in pairs actually makes the most sense, right? So if I take the number 36, obviously I could have 1 times 36. What else could I have? We're not looking primes necessarily here. We're looking for any combinations. What else could I have? 2 times 18. What'd you say, Sally? 4 times 9. Can I do one before that? There's one missing. All right, 3 times 12. Then you said 4 times 9. 6 times 6. And after that, it just repeats with the numbers flipped, right? So how many different possible rows and so forth can he have? Well, any of these numbers, right? So you might say he could have 2 rows of 18, but you also have somebody who's going to say, oh, no, he could have 18 rows of 2, Okay, we're not talking like that. I mean, it doesn't matter. It's an irrelevant point. Any of these are possible number of rows depending on how you're counting your rows. So he could have 1 row, 2 rows, 3, 4, 6, 9, 8, was 18 next? 12, sorry. 12, then 18. Or kind of he could have 36 rows of 1. You could argue that the 1 and the 36 kind of contextually are bizarro in this situation, but you could have 1 row of 36. All right, last question for today. Bob says that to check whether a number is prime, he just uses the divisibility rules he knows for 2, 3, 4, 5, 6, 8, 10. He says if a number is not divisible by these numbers, then it's prime. How do you respond? So it's a good idea usually to decide, is he right or is he wrong, as a first step in deciding how you're going to respond. Is his method going to work?
Is 49 divisible?
49 would be divisible by 7. So that would be an example, right? So you first would respond with 49 does not divide by these numbers. This isn't the only example you could use, but it's a good one. But it is composite, right? It's not prime, or you could say it is not prime. Sorry, I ran out of space. So the very fact that we can find an example that doesn't work for this is not good. There's other problems, even if we sort of threw 7 in here. Anything any larger than 10 is also going to fall into a problem, right? Like something that divides by 11. So imagine 11 times 13 or something like that, right? It's not going to work. Not only that, but he's duplicating some things. For example, if a number is not divisible by 2, is it going to be divisible by 4? Not a chance. So he's doing more work than he has to for some of these numbers too, right? So in some regards, he's missing numbers, but in other regards, he's got extra numbers that are not useful for the argument that he's trying to make. So some combination of those details would be a good response for Bob.